vamos a dar comienzo a este seminario. En esta ocasión tengo el honor de invitar a un buen investigador, que además amigo mío de hace ya muchos años. Voy a leer unas breves líneas para los que no lo conocen. El profesor Chedly Braham es investigador activo del laboratorio que se llama PIMM, que quiere decir Procesos de Ingeniería Mecánica y Materiales, en la Escuela de Arte Métier en París, Francia. Cuenta con más de 200 publicaciones internacionales. Su línea de investigación se centra principalmente en la coordinación de los procesos de fabricación y la microestructura y la durabilidad de materiales metálicos. Ha realizado contribuciones sustanciales en el avance de la técnica del análisis por estrés, utilizando principalmente diffraction de rayos X y diffraction de electrones. Durante 8 años dirigió el equipo de investigación MED-X, especializado en metalurgia y corrosión. También se desempeñó como jefe del departamento de materiales en el San París, o sea, donde trabaja, durante una década y ocupó cargos como experto científico y coordinador del departamento de ciencias para la ingeniería del Ministerio de Educación Superior e Investigación Científica de Francia durante 3 años. Es un placer para mí que esté con nosotros y espero que hagan muchas preguntas y que aprovechen la.
Great, thank you very much. Yes. First of all, welcome to you, and I would like to thank the staff of the Institute of Investigation in Materials. And I would like also to thank my colleagues Léon Morin, André Barsmonski, Abid Chidom, and Gonzalo Gonzalez for their contribution in the studies presented here concerning residual stresses analysis using diffraction methods in structural integrity and development of new processes. I will start by an introduction. And I will present you the effect of residual stresses, their definition, and the origin and classification of these residual stresses. And after, I will present 2 approaches to analyze residual stresses by numerical method and then experimentally. And I will present in the 4th point 3 applications. The first is using classical X-ray diffraction. The second using neutron diffraction, and at the end the synchrotron radiation. And before concluding, I will present some improvement concerning the classical X-ray diffraction method. So we know that manufacturing processes as forging, welding, grinding, cutting, machining, and use high level of deformations and heating, and this will lead sometimes to cracking or to residual stresses. We know, for example, in the case of welding or electric discharge machining, we can have some cracks during the process, or we can have residual stresses, and we know that residual stresses can have the Tremont effect, for example, and we know that tensile residual stress will reduce the fatigue life of component, and also they increase the sensitivity to stress corrosion cracking or hydrogen embrittlement. We can see in these photos the effect of turning. We can have cracks due to applied and residual stresses here. The effect of milling after corrosion testing. We can see here the net of cracking due to the residual stresses induced by machining. We know also that compressive residual stresses can improve the fatigue life in fatigue or in stress corrosion cracking. This is very old results where we compare as received materials after welding and a specimen after pinning, shot pinning. We can see that the shot pinning induces at the surface compressive residual stresses. So this improves the fatigue life of components. We can see here the as received materials. This is the Voller curve, and this is the improvement after shot pinning. So this is, we know this, So to reduce residual stresses, we can use some post-treatment, for example, heat treatment to release residual stresses, or we can also introduce compression by post-treatment, for example, by shot peening, laser shot peening, or polishing, and so on. We can see in this example that with grinding, we can have crackings after corrosion tests. And if after grinding, we make a brushing, we induce compression, and so there is no cracks after the corrosion test. Same results if we compare the surface after milling and surface after milling and laser shock. We have in the first case stresses, cracks and no cracks after, for the second case after corrosion test. Another effect, no less important, of residual stresses is the distortion. After rolling or forging, we can get residual stresses inside the materials. These residual stresses are equilibrated. So if we remove material after these operations, so we need another equilibrium. So this will induce distortion. For example, in this piece of automotive application, we can get some distortion after machine. So it's important to say that any material removal or plastic deformation by mechanical or thermal loading will modify the stress distribution. So it's very important to analyze the initial residual stresses and also its evolution during service or during machine, during any step before using. So let's see now the second point corresponding to the residual stresses. And first, the definition of residual stresses. So residual stresses are multi-action stresses existing in an insulated body, not subjected to any external force or movement or thermal loading. The origin of these residual stresses is a distortion necessary to ensure the continuity of the material and accommodate different states of deformation in contiguous domains. That means it's due to a gradient of deformation, heterogeneity of deformation. So to understand this, that means the origin of residual stresses, we can start by a very simple example. In assembly by bolt, we can see here that in this assembly, we have some parts in tensile and other parts in compression, and all the system will be in balance, in equilibrium. So the question is, what about the case of one component? For example, after machining or shot peening, welding, we get heterogeneous deformation or thermal gradient, and this will induce residual stresses. So we will find different effects at the origin of residual stresses: mechanical effect, thermal effect, and phase changes. Okay. So now let's see all these parameters, and first the mechanical effect. If we consider the case of shot peening or machining in gentle conditions, that means with very high efficiency of cooling, that is, in some cases we can get preponderance of mechanical effect. That means we can not take into account the thermal effect. So that means we will get, in this case, a gradient of plastic deformation. So, of course, we can make complicated analysis, and let's take a very simple consideration here. We can here consider that we have only two parts, the surface layer and the bulk of the material. That means we have here a difference between the deformation in the surface layer and in the bulk of the material. So if we make, for example, shot peening, we will have deformation of the red part. For example, if we have separated parts, we don't have any force, any residual stresses. But we have the continuity of the material. That means we will this deformation will be prevented by the bulk of the material. So we will have compression near the surface, and this will be calibrated by tensile stress inside the material. And of course, this is a sample example. And if we consider that we have a gradient with continuous variation, we will have such distribution of residual stresses in that. That means we have compression equilibrated by tensile inside the material. And now, if we consider now the thermal effect, for example, during welding or grinding with hard conditions, it means the thermal effect will be preponderant, that we will get here a gradient of temperature. But the same way, consider that we have only two parts, the surface layer and the bulk of the material. So we have the heating of the near surface. So if we start by initial temperature, T1, with the initial length, if we increase the temperature, we will have an expansion, but this expansion will be prevented by the bulk of the material. So that means we induce compression. And if this compression exceeds the yield stress, we will have reduction of the initial length. L0 becomes less than L0. That means this part will be intensified. So that means thermal effect will induce tensile residual stresses near the surface, and this will be equilibrated by compression inside the material. Of course, with the continuous gradient, we will have such profile with tensile near the surface, and this will be equilibrated by compression inside the material. We can add also phase changes effect. In this case, we need to consider the change volumes, and sometimes these change volumes, for example, when we have a surface quantity, we have these changes only near the surface, and there is no phase changes inside the material, so we can induce plastic deformation, so we get also residual stresses. And at the end, we have another effect. It's very particular effect. In the case of metallic matrix composites, and for this, we can have different phase thermal expansion coefficients. And of course, when you change the temperature, we don't have the same expansion, so we will have residual stresses. We call this second order residual stresses, because it's due to the difference between the behavior of two components of the materials. So we can say that in the general cases, the main source of residual stresses is the plastic strain heterogeneity. So now let's consider this heterogeneity. That means if you have some loading, for example, by torsion, by bending, you have heterogeneous deformation. So the case where you don't have this heterogeneity is the tensile test. In the case of the tensile test, if we have a heterogeneous material, if we make tensile test and we unload after plastic deformation, we don't have any residual stresses. But if we make the same test, but with materials containing some heterogeneities, for example, if you consider a part after grinding, for example, we can have a hardening of the near surface. So that means if we consider the surface layer and the bulk of the material, we have different behavior in tensile test. The surface, it will be harder than the bulk of the material. The macro behavior is an average of the two behaviors. And when we can see the differences of the level of the stresses when we apply a load. And if we unload, or in macro behavior, we have 0, but we can see here that we have a tensile residual stresses near the surface, and this will be equilibrated by compression inside the material. In this case, it's simple to make calculations because we are in this configuration. We consider here that we have homogeneous strain. That means we have the same size strain in all the material. But in other cases, for example, if we consider duplex steel, with multi-phase material, with austenite and ferrite. In this example, we can have 50-50%. And we have here, the ferrite is harder than the austenite. So when we make loading during tensile test, you will have more higher stress in the ferrite than in the austenite. And when you unload, you will have tensile in the ferrite, and this will be equilibrated by compression on the austenite. But the calculation of this will be more complicated because we are not in the case of homogeneous strain or homogeneous stress. So for this, we need more complex model. We use here, for example, self-consistent model to make all calculations. So here that we need to consider the residual stresses at different scales, macro stresses. The order one corresponds to the average in all the material or in one phase. We can call macro stresses or pseudo macro stresses. And we have also the second order due to the difference between the behavior of grains or phases. And if we observe inside the grain, we have some heterogeneities in the grain, and so we can have stresses at third order. And this can be very important to consider the different scales, because when we need to determine criterion for mechanical resistance or for fatigue or localized corrosions, we need to understand the mechanisms of the deformation and also of cracking at the different scales. We can observe, for example, in this example, that we have cracking in only one phase in this duplex steel. We can observe also that cracks will occur in some grains due to their orientation. So we can see now the methods to analyze residual stresses, and I will start by an example of study using the fine element method to simulate machining process. If we want to take into account the applied stress for design or sizing, it can be easy. We have methods to calculate this, but the problem is if we need to take into account residual stresses, we don't have strain gauge or sensors. We don't have the initial stress, the initial state, so it's complicated to analyze these residual stresses and to take into account in our calculation or sizing. So this is a study using the fine element method to determine the residual stresses after machining by turning. So the problem of fine element method is that we need to simplify the process. We need a model. For example, here we consider that we have an orthogonal cutting. So we can make calculation in 2D dimension and not in 3D dimension. And so we need also a protocol of calculations. This is different steps. We need to consider the geometry of the tool and the workpiece. We need to determine, to have the thermal physical properties, and also the mechanical behavior of the materials and the model of this. And this is very difficult because you need the behavior at different ranges of deformation and also at different range of strain rate. And then we can calculate the repartition of stresses, strain, and temperature, and so on. and also to determine the cutting forces. And after unloading, this is the second model, we can get residual stresses. And for all steps, we can compare by with the experiments, for example, by measuring cutting forces or measuring residual stresses by diffraction. So if the comparison is okay, that means we validate our model, and so we can determine the effect of each parameter of cutting on our residual stresses. So we can get, for example, in this case, or different conditions of cutting, and we can compare simulation and the simulation and the measurement, for example, of residual plastic strain, and also residual stresses in the two directions of the cutting and orthogonal direction. So now, what about the experimental methods to measure residual stresses? So a very simple method used in automotive industry is this method. For example, applied to brake disc, we just make a cutting and we see the opening of the tightening or distortion of the disc after cutting. And from this, we can determine if there is high level of stresses or low stresses. So this is very macroscopic and we have an average of what happened in one part. That means the question now is how to get more quantitative measurement, and also how to get the local measurement. That means, can we have in the in-depth stress gradient or the repartition in the surface of residual stress? That means, can we have a map? So, if we consider the different methods, we will find the mechanical methods. They are descriptive methods, and the principle is to remove the materials and we see what happened. That means we see the effect of the relaxation of stress. Means that we measure the distortion due to this removal of the material. So the measurement can be effected by different methods, by gauge or by other methods. And we have, for example, deflection method, incremental holding method, the Sachs method, sliding or contour method. We have some different methods, and also we have physical methods. They are not destructive, and the base of this is to measure the effect of residual stresses on many physics parameters. For example, we can measure the effect of residual stresses on the D space in diffraction, or we measure the effect on the propagation rate of ultrasounds, or the modification of magnetic behavior due to the presence of residual stresses. So if we compare now all these methods in terms of penetration depth or in terms of spatial resolution, we can observe here that if we use the different X-ray methods, it means classical X-ray, synchrotron, and neutron diffraction, we can see here that we cover a very large field on terms of penetration or in spatial resolution. So that's why we developed these methods, and we use all these methods to analyze the residual stresses for different studies. So first, diffraction methods, their base, their base is to measure the variation of D space due to residual stresses. So we can consider that elastic strain is D minus initial D by initial D. And in reality, this using the diffraction method, this will be measured by measuring the displacement of the peak diffraction. And to have sensitive method, we need to use a bright angle higher than 90 degrees. So we can use classical X-ray And we know that X-rays are strongly absorbed by the materials, metallic materials. So that means the measurement will be near the surface, typically 10 microns. And if we want to measure inside the material, we use neutron diffraction. The advantage of the neutron diffraction that we can measure in all directions. And we have an intermediate penetration is the synchrotron radiation. The advantage of the synchrotron is that we have a very high intensity. That means we can measure in a very weak fraction of the material. For example, if we have some particles, we can measure in these particles. The inconvenient is that the Bragg angle is very low. So that means it is not enough sensitive, but we can use it. So in our laboratory, we developed mainly the classical diffraction method, and this is now widely used in many fields. And for this, we can use classical 4-circle volumeter, or we can use portable devices. For example, here we use a robot. So for X-ray diffraction, we consider that we have a polycrystal material with fine grains because it's a statistical method, and we consider that we have homogeneous materials with isotropic behavior. So we use it many times, of course, for many applications. For example, for automotive, we can study the effect of machining, or here deep rolling on the crankshaft here. So we need to understand this to study the behavior and fatigue of this component. We have also some application for aeronautic field or for nuclear power plants. This is some example for measurement in situ. Now let's see some studies using these diffraction methods. And for this, I will present first a study using X-ray diffraction to study the effect of residual stresses on fatigue and on stress cracking corrosion. And then I will present a study using neutron diffraction to study a multi-phase material, this stainless duplex steel. That means we use this method to study the behavior of the different phases. And the third example is a case using synchrotron radiation. So concerning the effect of residual stress on fatigue, we know that the fatigue strength of the material depends strongly on the surface integrity. What means surface integrity? It contains the geometry of the surface, the topography, the surface texture, the hardening, the microstructure, the presence or not of defects, and the more sensitive parameter is the residual stresses. So if we consider this on fatigue tests, for example, here we consider the stainless steel 316L tests in fatigue. This is the Voyer curve. For a ground surface, we can observe here that if we compare this state to an electropolished surface, that means after removal of the layer affected by the machining, we can see here that we have an improvement. That means we have the reduction of the fatigue life by grinding. So this is attributed and due to the presence of high tensile residual stresses in the two directions of the machining and on the transverse direction. We have here the value of the tensile residual stress for the grinding in the classical conditions using soluble oil cooling. And now, if we reduce the thermal effect, that means we reduce tensile residual stresses. And using liquid nitrate, we have a beta cooling, and then we can see that we reduce the value of these tensile stresses. And now, if we apply brushing after classical grinding, we can see here that we induce a compression of the surface. So now we can compare the behavior and the fatigue. And so we can show that our initial state is the grinding with classical condition of cooling, and with liquid nitrogen we have improvement, and the best results are obtained using brushing after grinding. So we can see directly here the effect of residuation on the fatigue line. And now, okay, this is for fatigue line, for fatigue, and for stress corrosion tracking, we can see the same conclusion. We know the effect of residual stresses, the effect of the tension, and the effect of the compression. So the problem is when we make some tests for corrosion, we use many shapes of specimen. We can use tensile, of course, or bending. We can use U-bends, yeah, or to analyze the inside of the tube of the external skin, or externally use here serine, and to study the internal face, we need to use here the reverse U-bend. So all seems very simple, but the problem is how to determine the real residual stress state, because we need to take into account the effect of deformation and also the initial states. States, that means the hardening and also initial residual stresses. If you have, for example, a grinding at the beginning, what happened when we apply stresses? This is the first question. This is an example of the results using calculation by finite element analysis method, and also by measurement using X-ray diffraction at the apex here, at the external skin of the tube. So if we remove the surface, the affected layer by machining, for example, or by short pinning, we can see here the evolution of the hoop stress as a function of the tightening in millimeter here. So we can observe, for example, for 5 millimeters, that we have at the surface about 350 megapascal. But now, if we take sealing with aftershock pinning, we can observe here that with a tightening of 5 millimeter, we have 1,500 megapascal. This is due, of course, to the hardening of the surface. So now, that means if we want to improve some behavior of the material, for example, if we consider this, this is an application for nuclear power plants. We use for some pieces, bolts, and so on, hard nuclear alloy. This is X550 alloy. And we observed some cracks in this part, in the screw here, and also in the legs here, because we have the bending, so the external of the leg is in tensile, so we can have such cracks. So if we take this material after grinding, of course we have very high compression near the surface at the beginning. The question is what happened when we applied some stresses or some load. So we can observe here what the total stress. That means what we measure when we apply stress, the real stress. And now if we unload at each step, we can see the evolution of the initial residual stresses. And we observe that the residual stresses change very, very quickly. And this will be stabilized at a positive value, 500 megapascal. And we started from minus 900 megapascal. This is the conclusion. So now let's see the second study using here neutral diffraction to study the behavior of duplex steel. And the advantage of the diffraction method is that we can measure separately the stresses by measuring the evolution of elastic strain, by measuring the displacement of the diffraction peaks in each phase separately. That means we can get the evolution of the stress in each phase. So we can use X-ray diffraction or neutron diffraction. The advantage of the neutron diffraction is that we can measure inside the material, and this is not, the results will not be affected by the machining of the surface. That means we are inside the material, no surface effect. So we use neutron diffraction to study the stainless steel, with 50% austenite and 50% ferrite. This is obtained by the balance between gamma gen elements and alpha gen elements. We have here the equilibrium between chromium and molybdenum and manganese and nickel. To study the behavior of each phase, we need a model. For this, we use the self-consistent model. And for this model, we need some information concerning, first, the orientation of crystals. And we need the elasticity of crystals and the system, slip system for the two phases, and also the hardening matrix. And now, if we measure what happened during the loading by diffraction, and we compare by the self-consistent model, then we can obtain the different parameters to have the behavior of each phase. That means we need here the critical residual, the critical shear stress, and also the hardening parameters for the two phases. Our first results are made using neutron source of LLB at Saclay near Paris in France. And for this, we use classical neutron. And for this, we use only one reflection for each phase, 111 for gamma phase and 111 for alpha. And now, if we apply stress, we can measure here the elastic strain. That means we can calculate stress after this as a function of what we apply, that is the macro stress. And we can have here this in two directions, in the direction of the loading and the transverse direction. So if we observe what happened in the applied direction of the stress, we can observe here that at the beginning we have a linear behavior, similar behavior for the two phases. And we can observe a first critical point corresponding to the beginning of the plastic deformation in the softer phase. Here it's the austenite. And so then we have stabilization of the stress in this phase and an increase in the others, means in the ferrite. And when we reach the second critical point corresponding to the beginning of the plastic deformation in the alpha phase, so we have again an increase of the stress in the gamma phase. So now if we compare the diffraction data and our model, then we can get the different parameters of the two phases. We can observe that the critical shear stress is higher for the ferrite than for the austenite, and the hardening is higher for gamma than ferrite. So that means we can, after draw any curve of, for example, the tensile curve, you can see the behavior of the ferrite, austenite, and also we know the orientation of our crystals from the beginning of the model, so we can get the distribution of the stresses in the two phases as a function of the orientation of the grains. So we can see that we have a very large range of values of stresses. The second study for this is based on the use of technique time of flight method. And for this, we used the spallation source of ISIS in UK. And the advantage of this method is that we can get simultaneously all the spectrum of diffraction. Means we have information of all peaks for each phase. And for this, we have a source, and we have two fixed detectors, the left one and the right one. You can see here the photo. This is the source of the node, a river, and we have the two detectors, the left one and the right one. And at the middle, we can put big machines to make tensile tests or compression tests. And this is some results of the testing by tensile test or compression. This is the results for the austenite, this is for the ferrite. You can see the evolution for each reflection. We can observe here the anisotropy effect. For example, if we see only for one case, this is the tensile test for austenite, we can see the main reflections here. We have here the effect of the anisotropy of the crystal. And after we can observe also the anisotropy in the plastic deformation of the field. And now, if we compare here the data of diffraction and our model, we can obtain different parameters, and we can see here that we have an acceptable agreement between the two. And now, the third study use X-ray synchrotron radiation to study the stress repartition between the ferrite and the cementite in perlitic steel. The perlitic steels can present very fine structure, and this is this material presents very large field of application and a very large range of strength, because it's the structure and the behavior is very sensitive to cold bonding and heat treatment. For this study, we used steel containing about 1.7% carbon, and we tried many heat treatment conditions, and we can compare only two conditions of treatment. For this treatment, we have always 100% perlite, but we have little differences. Difference here is the interlaminar space. We can observe here the difference between the two treatments, and this gives very important differences in fatigue behavior. And this is the example of only the tensile curves. We can observe here that the yield stress change is higher for the finest structure, the red one. We have 500 megapascal, and for the other we have 400. So this is very important, and we need to know here the behavior of the perlite. So it's very difficult, because in some cases you can make some micro hardness, but in cementite it's very difficult. So there is no data about the behavior of cementite, and here we need to understand the effect of the hardening by the cementite. We have, of course, the composite effect, but also we have a structural hardening due to the presence of these carbonates. So the problem here is that the fraction of cementite is very low. So that means we need to use a synchrotron radiation, because the intensity will be high. So that means if we can have some information about the cementite. And for this, we use the source of SRF in Grenoble in France, and we use very high energy and relatively small beam size, and with high energy we have very low angle brightening. So but this will be compensated by the use of 2D detector, means we can have information in many directions, and also a very high distance between our specimen and the detector. So using this high intensity of synchrotron, we can, of course, we have in the spectrum here the different peaks of the ferrite, and we have a relatively low intensity for cementite. And if we make magnification, we can see that the peaks of the cementite can be treated. So if we apply the law, we can see the evolution of the peaks and the displacement of the peaks for the cement. That means we can get now the behavior during the inside test of the diffraction of the different radiations for the ferrite and for the cementite. And so we can observe here the evolution before the plastic deformation and after. And of course, we can now compare to the model, self-consistent model, in terms of the elasticity and also in plasticity. We can here see the epsilon 11 and epsilon 22 during the tensile test. And the problem here is that self-consistent model, we have good fitting at the low range, at the range of low deformation, but for higher deformation, we have high differences. So we need to improve our models. For example, here we use the mixed model to have better results. We will continue for this, of course. Now, before conclusion, I would like to present you a new development of a classical X-ray diffraction method. We have this classical method that the possibility to have this in-depth distribution of residual stresses using diffraction and electropollution. We move layers and measure, we move so we can get the repartition of residual stresses between the surface and in depth. We can reach, for example, in general, 0.5 millimeter, but in some cases we can go to 1 millimeter, not more. And we can have, for example, this is the profile for as minute. This is after laser cleaning. And the question is, can we have better resolution, spatial resolution? We improve this by using grazing incidence. And for this, we measure in very outer layer, in this part, using multi-reflection incidence. We can compare here what we measured by this technique to the standard method. So we have the possibility to have very, very nice, very good spatial resolution to measure in depth. But the problem is, if we have a surface gradient, we have a very poor resolution because we have relatively big size of the beam. So we can, of course, reduce the size of the beam, but we have always some averaging. We cannot reduce the big size because if we reduce, we will have only few grains. That means we will need very, very fine microstructure. So there is some limits. So for this, we developed a new method to rebuild the residual stress map or line from average measurement. That means we need, for this method, to determine the local stress from the average method. For this, we consider that we have regular measurement, and then we can use an inversion of the system to get the local stress from the average value. But for better results, we need to measure using two different spots. We applied this to a process of severe plastic deformation process. This is the RCS process. And for this, we studied this process, and also we make some simulation of this process. This is a simulation using only one pattern here. That means from finite element method, we can get the repartition of stresses, strain, plastic strain, displacement, and so on. This is the map of the stresses at the surface of this one pattern. If we consider a line, we will have some variation of the stress in this pattern. This is the results of the calculation from finite element analysis of the residual stress in one line. So the problem is, if we use a spot size of 2 millimeters or 4.5 millimeters, we will have an averaging effect. So that means if we measure in different points, for example, with very regular grid, we for higher size we have very high averaging. So the question is how to determine this profile from these profiles. We use it for this our method, and that means this is what we measure by X-ray diffraction. For this, the small size, we have the blue curve, and for the bigger, we have the red curve here. And from the two, we have the, you see here, the black line. This is the profile repeated from the two. And then we can compare this profile, the black one, to our reference obtained by calculation. And also we can compare also the measurement directly to average profile obtained by calculation. We also extend this approach to the mapping to the dimensions, and we observe here the problem is the number of points. The method can be very long because if we use here 50 by 50 points, this we have 2,500 points. Each point can take perhaps half an hour or more. It means very long time to get this. This is an inconvenience of our method, but this is the map used by the small spot, and this is for the higher spot. From these two maps, we can obtain this one, and then we can compare to our reference obtained by finite element method. Okay. So we can conclude. Okay. So we noted here the effect of manufacturing process to generate plastic deformation and thermal gradient. So we said that for structural integrity, it's crucial to determine the distribution of residual stress and also their evolution during the service. The diffraction methods offer a large range of spatial resolution and depth penetration. We demonstrated here that the diffraction method is suitable to have the behavior of each phase in multi-phase material. And also we saw the advantage of the grazing angle incidence geometry, and also the method, deconvolution method, to improve the spatial resolution for lateral gradients. This is my conclusion. Few words for the future. And thank you for your attention.
Much. I don't know if you have a question. Please.
For the talk, it's very interesting. I have a question in the last part in the XRD for the variation of the penetration depth, how large or small is the grazing angle variation?
Concerning grazing.
Uh-huh.
Okay.
The last.
No, this is not enough. You talk about the grazing incidence.
Yes.
So in standard method, you have the incident beam and the vector beam. And to make measurement, you measure always in the normal direction to crystals. So that means if you want another direction compared to the piece, you need to make a tip or the piece as you wish. And that means you change this angle of sine. This is the tip. And if you change the tip, you change also the penetration. This is the standard method. With the standard method, you have to determine average. The average is, for example, if you make measurement for steels or a limit for steels, penetration is about 6 to 10 millimeters. This is the average. Okay. And for grazing incidence, this is very more firm. This is more constant incidence speed. And the tip is obtained by using different reflections. That means in this case, you use only one HKL length, it's the same. So the calculation is very simple because you use only one elastic constant. That means you can have linear correlations also, so mathematically it's easy. But this here is more complicated because you use different HKL. That means it's like if you use different approaches with different initial number. But the advantage is that if you use constant alpha, you have relatively constant penetration as a function of psi angle. And if you change the angle, you change the penetration. And also you can combine the effect of angle and radiation. You can use, for example, copper radiation, ion radiation, and so you can have different wavelengths. We use also synchronization of this technique. You can change the wavelength, so you can have gradient without any removal of material. This is an advantage. This is non-destructive.
Thank you. Very interesting why the subjects in this outcome. My question is about when you talk about these paralytic steels. Yes, but you have two different structures. I mean, in the steel.
The paralytic steel.
Yes. Do you found some phase transition during high stresses? High stresses.
There is some strange things. So the problem is you see here the increase of the load. At the end, you cannot see any peaks. It's like if there is cementite disappears. I read something about this, but not easy to see. Okay. And in cyclotron, we used 30 seconds for each peak. And in general, so we have very high peak of ferrite, and this is not usual. Usually people use few seconds for one peak. For 1 second, 1 second, 2 seconds for peak. 30 seconds was very.
What were you showing in the beginning? Not 22. You found that you have the X-ray diffraction peak without and with the internal stress, and that doesn't mean that the crystal it has growth with the formation. That because your peak goes to the low angles after the formation. And
in which case?
No, 22.
22. Sorry? Yes.
Yes, or you have the point after the stresses, your
Stress. Yeah.
it goes to lower angle. No?
Yes. Yeah. Like this. In diffraction. It's possible because in X-ray diffraction, the problem with X-ray diffraction depends what we. I don't remember what is the fix. You measure in general the Poisson effect because if we make tensile test, you measure here. So there is mice in the fold. Because you measure, in reality, you measure always epsilon 3,3, it means normal stress. If you take your reference on the crystal, they are always normal strain, and from normal strain you have stresses. And in reality, if you write the equations, sigma epsilon 3,3 is sigma 1 plus sigma 2. So you measure this. And the question is how to get sigma 1 first and sigma 2 after.
Well, maybe one last question. Yes.
Thank you so much for the talk. So I have a question about the synchrotron experiments.
Yes.
As you mentioned, it's very high energy. So my question is if you take into account the radiation damage, like making a blank experiment without any deformation.
Yes.
Did you make the experiment without any deformation, only taking into account the radiation damage from the high energy from the synchrotron radiation?
There is no damage. What we measure, of course, we need the initial state. It is the problem of the initial state. That means the space for free stress specimen.
Yes.
So the diffraction method is a relative method. That means you have initial and you measure the variation. So for synchrotron and neutron, we are inside the matter. That means we can have really triaxiality of stress in sigma 1, sigma 2, sigma 3, it's all components. So for this, we need, in theory, the D0. That means, of course, in our study, we start from initial state and we increase the load and we measure stress. So there is no problem because for this, we consider that we don't have residual stress. But the problem is for duplex MSC with terminal history and so on, you cannot say that initial stress is equal to 0. There is some problem due to the second order stresses due to the difference of the range. This is a big problem. For classical cases, we need D0 for neutral diffraction. We can take powder, we can make, for example, for all the section, we consider that we have the balance of stress, so we calculate and we determine what the D0, the initial D0. That means we make a correction of our measurement. But for classical method, using classical X-ray diffraction, laboratory method, it's easier because we can consider that at the surface, we don't have any stress. We have only pressure, is nothing, 0.1 megapascal is nothing. So we consider that normal stress, sigma 3,3 on a piece, is equal to 0. And also d sigma 3,3 by dz, that means the gradient at the cell is equal to 0. That means in 10 microns, the sigma 3,3 is always negligible. You can have only triaxiality if you have some cracks or something like that. So that means we can consider that normal stress is equal to 0. If you consider this, the calculation can be made without D0. Because we use only only the slope of the curve. No, we don't need a reference. And so this is not one. So we used also measurement from X-ray in some cases to have the D0 to make measurement by unit of diffraction or synchrotron.
I think it's